Okay, welcome to experiment number 10. This is the experiment where we measure the low frequency response of a common emitter amplifier. So we're going to start with our good old friend, the amplifier that we did in lab 8. And I think you've also done homework on this. You should be pretty familiar with it by now. But now what we're going to look at the effects of C1, C2, and CE on the low frequency response. And so to come up with our predictions, what we would like to do is start with the DC analysis we did before. We're going to be setting this specifically for an ICQ of 1 milliamp here. So we should be measuring 1 volt DC on the emitter, about 1.7 on the base, and about 10 volts on the collector. So we'll be setting that for the very first thing we do. Then from that, we can come up with our GSM and our RPI. And for this lab, we're going to ignore little RO just because it's 100K, it's pretty big, and it really has very little effect. So from there, we now have our AC model. And the AC model has all 3 capacitors in it as well. This one is C2 over here. Let's fill that one in. Okay, and so I drew this with the ability to open or short any capacitor. So what I'd like to do to hedge all of our bets is to calculate the pole frequency of C1, whether CE is an open or a short. And it turns out C2 has no effect. So we're going to calculate the pole frequency of C1 with CE shorted, and this bypassed the ground. And then we're going to calculate the pole frequency of C1 with CE open and treating RE as unbypassed. We'd like to do both cases just in order to get what range of frequencies we can expect. In reality, CE would be somewhere between an open and a short, and our pole frequency would be somewhere between those 2 limits. Same thing with C2. We'd like to calculate the pole frequency of C2 with CE open and shorted, and it turns out in this case it makes very little difference because RO is 100K and RE is only 1K. So whether or not the 1K is in the picture doesn't really matter. So we're only going to need to calculate 1 pole frequency due to C2. And then for CE, we're also going to calculate the pole and the zero depending on C1 open or C1 short. CE does not really see C2 because it's isolated by this high resistor over here. So we're going to calculate the pole and the zero of CE, both with C1 shorted and C1 opened. And again, C2 does not really affect the pole and zero of CE. So here are our equations with our REQs for the pole of C1. REQ is equal to RS plus RB parallel R pi if C is a short, and RS plus RB parallel with R pi plus beta RE if CE is an open. Okay. For C2, REQ is just RC parallel RO, but we're going to ignore little RO. If you wanted to include it, this is where it would go in series with RL. And for CE, the REQ is just RE, whether C1 is an open or a short. And for the zero frequency, for the pole frequency, REQ is going to be this, RE in parallel with R pi plus RS parallel RB over beta. If C1 is a short, that means that RS is now in the loop. And if C1 is an open, the circuit stops here. It's just going to be RE parallel R pi plus RB over beta. We are using a beta of about 250, which seems to be a widely measured value that we got from lab number 7 for these transistors. And so that's the value that I used. So from here, I would leave it into you as your pre-lab to calculate all of these pole frequencies and the zero frequency as well. And that way you can build your circuit and kind of know what to expect. The question now remains is how are we going to measure these low frequencies? Because these, in some cases, will be very slow waves and they're hard to see. So we're going to have a different approach for each one. What I would like to do is look at a frequency response. I'm just going to erase, I think I'll just erase the bottom one since it served its purpose. The strategy that we're going to use to measure our pole frequencies is this. Let's say we have a pole and another pole, and then CE gives us a pole and a zero, like that. What I'd like to do is, it's hard to look at this pole because it's going to be affected by the other 2 poles. So what I'm going to do is I'm going to take a pole and slide it off to the left so that it gets itself out of the way. We cannot look at this pole here because this pole is messing it up. It's bringing us way down to there. So what I'm going to do is I'm going to temporarily slide this pole far to the left, about 2 decades to the left. And the way we do that is we're going to replace the capacitor, 1 microfarad, with a capacitor that's 2 decades higher, 100 microfarads. And what that'll do is that'll slide this pole out of the way so that we can look at the other two. So we're going to do that one at a time with the poles. We're going to look at, actually we can look at C1 directly. We're going to look at the voltage here and the voltage there and look for a 0.707 drop. But for CE and C2, we're going to slide C1 out of the way and slide C2 out of the way to look at CE. We're going to slide CE out of the way to look at C2. So again, the way we slide a pole out of the way is you replace this capacitor here, which was originally 1 microfarad, with a 100 microfarad capacitor, and that is going to slide the pole 2 decades to the left, and now it'll be clear to look at these two poles by themselves. So that's what we're going to do. Once we get to the bench, we'll build this circuit, set the DC Q point. You'll need that to measure a value for R2. So R2 is going to allow you to calculate values for RB throughout these calculations. And then once that's set, we're going to measure our gain. Okay, we're going to measure our gain. And then once we have the gain, we can now start to look at our 3 poles due to C1, C2, and CE, and see how closely the measured frequency you get in lab matches the frequency here that you calculate. So what you should have in your results section is, once again, a table. So this is going to be C1, C2, CE, and pole frequency with cap open, pole frequency cap closed, right? So we have an open and closed case here, and an open and closed case there, and then FZ. And then we're also going to have a comparison of calculated versus measured. So in your table, you're going to organize C1 and C2 and CE under these conditions here, and you'll have your calculated pole frequency or zero frequency and your measured pole frequency or zero frequency. And then you're going to see how these two compare. It would also be nice to give a % error between these two to see how close we got it. As far as sources of error go, there are quite a few. Our beta could be off because we're dealing with different transistors. Also, as we'll see with the oscilloscopes, slow moving waves are difficult to measure on an oscilloscope because the oscilloscope itself doesn't like to trigger on slow moving waves. And when you have the scope on AC coupling, it has its own low pass filter, a high pass filter built into it as well. So we're going to have to observe all of our waveforms on DC coupling so that the built-in high-pass filter, the scope, does not interfere with our measurements. So we'll have waves that go way up off to the top of the screen. So, but this is just a typical difficulty. It's nothing we can't handle. But your results should be in a table that looks like this. And then somewhere you put calculated and measured. So calculated, measured in each box that we fill up. So on your results section, all I want to see is a table. I don't want to see any text, any writing. I just want to see this table for your results. And then you can, anything you want to talk about, that goes in your discussion. Okay, so at this point, we're going to put our circuit together, bring it to life, and take some measurements on it. Okay, so here we go. We are seated at our usual lab station. We have with us breadboard number 5, which has been pretty lucky for us so far. We have the Keysight 33500B series waveform generator. We have an Agilent E number 793. We have an Agilent E3620A dual DC power supply number 688. We have a Fluke 189 digital multimeter number 0458. And we have a Tektronix 2012 mixed signal oscilloscope number 635. So let's first just turn the machines on and let them warm up while we build our circuit. Okay. And so we're going to start with our transistor. Looking at the flat side, it goes EBC. So let's plug that in first. And I like to plug it in so that you can actually recognize it. Now from the emitter going to ground, we have a 1K resistor that's brown, black, red. This one will do. The leads are a little bit bent up. We'll see if we can get them to cooperate. So the ground lead is the lower bus. Here's the emitter resistor right here, plugging into the lower bus. Okay, and let's plug in our emitter capacitor CE right across the emitter resistor. So it looks like we're just building this one from the bottom up. Now the capacitor is tied to ground, but just a point of trivia, you could plug this capacitor into VDD and it would still do the same thing. Okay, so we have our R1 is a 100K resistor going from the base up high, base to our VCC, the upper bus. Okay, and then we'll put the pot in later because it's bulky and it kind of gets in the way. And then we now have our collector resistor, our first one, a 10K, brown, black, orange, going from collector to high. Let's put that over here also. One reason that people from Japan make such great electronics is that they have small hands and they can do this much more easily than I can. So one of my cultural disadvantages. Okay, so here's our RC going up high, and then we're going to go through capacitor C2 from the collector off to the side. And then we're going to have our other 10K resistor being our RL. That's going to go from C2 to ground. Over there, that's in place. And then all that's left is our C1 and R1 and the potentiometer. So here is our RS that goes from the signal generator. We're going to just put that off to the side. And here is our C1 that goes from RS to the base, like so. And now we can connect up our signal generator. We have our coax. We're going to plug it in here, and we're going to just clip this lead to ground. We'll put it there temporarily. And we're going to clip this lead onto the resistor, like so. So we have VS coming through RS through C1 to the base of the transistor. Okay, and then from there we have R1 going up. R2 comes down, so here's our pot. I'm just going to center the pot before I plug it in. This is an older pot. The older pots are made a little bit better than the newer ones. So this one is a real survivor. So we're going to plug that in from base to ground, and we're doing that last because it is kind of in the way. It's big and bulky. What we could do is once we set this to a value, we could just go off and get a discrete resistor and put it in its place. And that should be all we need for now. We just need to connect up our power supply. So our ground lead, the signal generator, the power supply is already wired for a plus output here on V1. You can tell because the negative is tied to ground. So let's plug that into the ground lug. And then the positive one, we're going to set it before we plug it in. So we're going to set V1 to 20 volts. That is the power supply for this experiment. Okay, and that's going to come over here to the positive lead. And then let's go ahead and set up our scope. So yellow is channel 1, blue is channel 2. Okay, and we're going to connect channel 1 to the right side of RS. The yellow one goes to the right side of RS. I like to clip it onto the resistor because it's a thicker wire. It's just more solid when you grab hold of it. And the output is going to be across RL, which is all the way over to the right here. And let us ground the scope probe over to there. So at this point, we should be ready. So we have a power turned on, plug it in, no smoke, that's good. And we're going to set our input signal here. What I'd like to do is make sure we're squarely in midband. So what I'd like to do is turn on output, and let's set it for 5 kilohertz. So parameters, okay. Now the scope is not making a very good picture of that. Let's find out why that is. Oh, because the output's not turned on. Let's see, is it on? So waveforms, channel. Okay, it looks like it is turned on. And then why is the scope doing that? Let's make sure that the averaging menu is off. Okay, it looks like it's on right now. Let's shut it off. That's better. Okay, so we now have a wave, but it's not triggering on it particularly well. So now let us set the trigger 1. And now at least it's holding still. But it's still not real happy, but that's okay. We have a pretty high gain, so the input's going to have to be small. So what we'll do now is let's set our DC operating point and get it to 1 milliamp. Right now there's no output, but that's probably because the R2 is not set correctly. The transistor is not biased correctly. So we're going to put our multimeter on DC volts, and we're just going to temporarily put this on the emitter, right? Not there. Oh, that's right. We need one more banana plug. Where are they? Oh, actually, there's one here. There's one here. So let's ground our voltmeter, but let's ground it over here just to keep it away from the circuit board. So we're now going to set the potentiometer to put 1 volt on the emitter. And it looks like it's, oops, it would help if I plugged in the power supply in the right place. Okay, so now let's see, we got 20 volts coming in, that's good. So now let's set the emitter, so let's see where the emitter is. The emitter is at 1.5. Let's bring that down to about 1. Okay, that's about 1 volt. And as you can see, we've got a nice healthy wave on the output. That's good. If anything, it looks like we're overdriving it. And let's now set our triggering back to channel 2. Because it's a much bigger wave, it's much easier for the scope to grab it. Okay, so we now have a very big wave. This is 5 volts per division. This is 1/10 of a volt per division. And we're overdriving it. So what I'd like to do is cut the input signal down in amplitude, parameter, amplitude, to make it so that the output here is coming through undistorted, even if it's not making a full blast output. That's okay. So now we've turned the input way down, but we've got a nice undistorted output. And this is a waveform we can trust to take measurements. Let's go ahead and just check the DC levels on the base and the collector. The base should be sitting at about 1.7. 1.58, that's pretty good. The scope didn't like that. And the collector should be sitting at 10, 10.9. So we're very close to our original bias point, which means our G sub M is going to be accurate. So we are now done with the meter. We can turn this off and we can go ahead with our measurements. So right now we're running at 5 kilohertz at 20 millivolts peak on our scale here. Very small wave. To measure that is not going to be very accurate because it's so fuzzy. So let's put the averaging back on. We're going to go to the acquire menu, averaging back on, and we'll see that that cleans up the waveform nicely. So now that's a waveform measurement that we can trust a little bit more. Okay, so the question is, are we in midband? We're very close to midband. It's not quite 180 degrees out of phase here. If we move these waveforms together, you can see that the top of the blue does not really line up with the bottom of the yellow. But it's not that far off either. I wonder if going to a higher frequency is going to make that better. Let's go to 10 kilohertz. we still have a little bit of phase shift in there. We're not perfectly in midband, but 10 kilohertz, that's probably about as high as I'd like to go. So we're not quite in midband. This is something you could write about in your report, saying that we are not perfectly inverting here. We have a little bit of phase shift, but our measurements still should be okay. All right, so let's slide this back up. Okay, and let's go ahead and measure our overall 3 dB frequency. So actually before that, let's measure our gain. Our output voltage here is 4.39 volts. Our input voltage is 35 millivolts. So 4.39 divided by 35 millivolts is our mid-band gain. It's about 120, 130, give or take. So we're getting a pretty good amount of gain out of this amplifier. And the reason we wanted to remember that is because when we're measuring our pole frequency, we're going to look for that to go down by 3 dB. So if we're starting with a gain of 4.4 divided by 0.035, what kind of gain does that give us? 4.9. Okay. So I should have prepared that also. 122. Okay. So the question is, how do we know we've reached our pole frequency? We've reached our pole frequency when the output here drops by 0.707. So if this is 4.39, let's just round this up a little bit. Parameters, amplitude. Let's be a little bit more precise. Let's maybe bring this down to 4 divisions. So we're going to make it just a little bit smaller. Okay, so right now what we're doing is that waveform is 4 divisions high. From bottom to top, that's 1, 2, 3, 4 divisions. So for this to go down by 3 dB, it's going to go from 4 divisions to 0.707 times 4, which is 2.828 divisions. So what we're going to do is we're going to bring the frequency down until this output waveform here measures 2.8 divisions. And that will make a note of our frequency. That is our overall 3 dB frequency. So again, what we're doing is we have our output here going full blast. When this goes down by a factor of 0.707, we have our overall 3 dB frequency for the lab, our overall low frequency limit. And then we'll pick it apart and look at C1 and C2 by themselves. So now let's take our frequency and start to bring it down. We're at 10 kilohertz. And it looks like the wave is still holding steady at about 4 divisions. But now it is starting to come down. That's the problem with averaging. It takes a little while. Remember, we're going for about 2.8 divisions. Let's see if we're close to 2.8 now. I overshot. Okay, so now we're at, let's just increase our precision here. Let's go to 3.1, 3.2, 3.3. Right about there? All right, so we're at 2.8 at about 4.3 kilohertz. So that means our overall frequency limit is about 4.3 kilohertz. Now what I'm hoping will happen is that one of the pole frequencies that you calculated due to C1 or C2 or CE is going to be somewhere in the ballpark of 4.3 kilohertz. So if it is, then we will have gotten our dominant pole, the pole that is the first one you come to as you bring your frequency down. Okay, so let's go back to 5 kilohertz. Actually, we're at 10 kilohertz, weren't we? Okay, now what we're going to do is let's look at our poles one at a time. So let's look at C1 by itself. So to look at C1, what we're going to do is we're going to put a probe on the left side of C1 and a probe on the right side of C1. And when we get a 3 dB drop across C1, we'll know that we have hit its pole frequency. So we've already got a probe on the left side of C1. Let's move this probe here to the right side of C1. And we're going to now look for, we have to turn the amplitudes way up and try to get this to show up. And for this, we can turn our input signal way up as well. So amplitude, let's go. For this, we don't care if the amplifier is clipping. So channel 2, let's see if we can get that to show up on the screen. There it is. Okay, and it looks like we're overdriving a little bit, so we're driving the transistor into saturation. Let's see if we can get these waveforms to the point where they're not distorted. Okay, so what we're looking for now is the frequency where this one is 0.707 times that one. So the yellow wave coming in is at 174 millivolts. So 174 times 0.707 is, calculator, oops. That's not what I want. 174 millivolts times 0.707 is, no, I don't trust that. 174 times 0.707 equals 123. So what we're going to do now is we're going to turn this frequency down until the bottom waveform means 123 over here. So again, we're going to bring this frequency down until the bottom waveform here reads 123 millivolts. So we're going back to frequency. We're going to start to bring it down. And keep an eye on this blue number over here. We're trying to get that to 123. It's coming down, but it's not in much of a rush. And we're down to about 1.1 kilohertz now. And let's keep this on the screen. Okay. We've come down to 100 hertz. Did these signal generators not go any lower than 100 hertz?
They should.
They should.
Your resolution now.
Okay, good idea. We're down to 10 hertz.
Oh, you're way below now.
Okay. Okay, now it looks like we've lost the triggering on channel 2. So let's go back to trigger on channel 1. It's a little bit bigger. And see if we can get this to hold still so we don't get a headache. Okay, triggering. It still doesn't like it. We're triggering on channel 1. We just want to get the waveform to hold still. Maybe if it was bigger. Okay, I mean, we can measure these waveforms as they are, but they're noisy. It won't be very reliable. So there are some options in the trigger menu. Oh, we can actually, we can do storage as well. But let's do trigger. Let's see if that makes a difference. It holds still for a moment, but no longer. Okay.
You could try the sync output from the function generator.
Good idea. Yeah, why don't we try that? So what we're going to do now, because the scope is not able to grab this waveform, it's too small, so we're going to do external triggering. That means we're going to use the sync output from here to the, oh, right, thank you. We're going to run from the sync output over here, and the sync output just puts out a square wave to the auxiliary input over here. And we're going to go to the trigger menu, and we're going to do source now. Yeah, there we go. Oh, okay. Oh, no wonder. Okay. Is the trigger output on? Trigger setup. No delay. That's all right. That's better. Okay. So now we have this triggering off a square wave that comes out of here. It's a good thing to know. And remember, we're looking for 123 millivolts there. So let's go back to our frequency. And it looks like I overshot. We're going to have to bring it the frequency higher. It's awfully slow to respond. I'm going to take the averaging and make it less dominating. So averaging record length. No, we don't want that. Let's see if that makes a difference. Okay, so we now have overshot again. So we want to bring the frequency down till we get to 123. That's better. It's responding a little quicker now. So what I did is I changed it so that instead of averaging over 64 samples, it just averages over 16 or 32, and the waveform comes back more quickly. So we're at about 117. We want to go for 123. That's probably about as close as we're going to get it. So there we're at 123, and this is at 14 hertz. So this tells us that C1 in actuality has a pole of about 14 hertz. So I would write that down as our measured C1 pole. Okay, so that's our pole frequency due to C1. It's usually easier than this. So, all right, let's go back and measure the frequency now of C2. So we're going to put channel 2 back on the output where it was before. And we can probably shut off all this funky triggering that we did, although the external triggering seems to work pretty well. Let's okay, that's all right. And let's do the acquire. That's okay. Let's just shut off the averaging for the moment. Okay, now we're having the scope doing something I've not seen before. Okay. All right, so now to look at C2, what we're going to do is let's move C1 and CE out of the way. So I still don't really like this display. I'm not sure. Okay, so I think we're kind of back where we're supposed to be, except this looks nothing like, oh, it's at 1 kilohertz, okay. All right, so let's go back to 5 kilohertz. See if we can get into mid-band condition. And it looks like we are, but we're overdriving, so amplitude. Let's get it out of the point where it's clipping. Trigger, source, channel 2. like so. Okay, so we're now back to our kind of normal operating conditions. And what we're going to do is we're going to look at the pole due to C2. So the way to do that is we're going to replace C1 with a capacitor 100 times bigger. So for that, I got these big old electrolytic capacitors. These are 100 microfarads. And technically, we don't really have to unplug C1 to replace it. We're just going to plug C1 directly on top of it if I can find a vacant hole to put it in. So it looks like C1 goes from there so I'm just going to plug C1. Now this has a polarizing stripe. The stripe is the negative terminal. The negative terminal goes toward the RS. So here is C1 from there. It's a little bit cramped in there, but we'll see if we can get it in. Okay. So now C1 has been raised. Oops, nope, I need to go one hole over. Yep, okay, so C1 now goes from RS to the base. And what this means is that the pole due to C1 is now slid all the way to the left. And we're going to do the same thing with CE. CE goes across RE. That's this one here. We're going to place another capacitor there in the place of CE, and that means that C2 will be by itself. So in this case, I'm just going to unplug it because I ran out of holes here. CE to there. Like that. So now we can be sure that the emitter is completely bypassed. And so the only pole we're going to see now is due to C2. C1 and CE poles have shifted all the way to the left, and we're looking at C2 by itself. So there's still a little bit of distortion in here. Let's reduce our amplitude a little bit. Like so. And right now we have an amplitude on channel 2 of about 5 divisions. So let's see if we can get that back down to 4 divisions. That's 4 divisions there. So all we're going to do now is bring the frequency down until we get to 2.8 divisions. Same thing as we did before. So frequency right now we're at 5 kilohertz. We're going to bring that frequency down until the blue waveform measures 2.8 divisions. So we now have an amplitude of 4 volts peak to peak, and we're going to turn that frequency down until that reads 2.8 volts peak to peak. So right now we're at a frequency of 5 kilohertz. We're going to start to bring the frequency down, and let's adjust to keep the waveform completely on the screen. And right now we're still at around 4.8, and we've dropped below 1 kilohertz. Okay, now we're just starting to come down. We're down to 100 hertz now. And 3.6, 3.5, 3.4. .84. Let's see if we can get a little bit more exact. Right about there. So that's at about 48 hertz. So what we're getting for C2 is a pole frequency at 48 hertz. Okay? So that's the second measurement, and now all that's left to do is CE. So to do CE, what we're going to do now is put our original capacitor back into CE. So that goes from emitter there to ground there. And we're now going to put one of these big monster capacitors in the place of C2. So let us unplug the C2 capacitor and plug in one of these big ones. And that means that the pole due to C2 is completely out of the way also. Okay, so all that's really left now is CE. So let's go back to 5 kilohertz frequency. Okay. So we're now at 5 kilohertz. And so what we should be seeing due to CE is flat, come down, and then level off again. Or we may not be able to see the 0 due to CE, but we should be able to at least see the pole. Okay, so right now we are at this level of amplitude here. Let's see if we can bring that up to 4 volts, to 4 divisions. Right about there. So we now have the output at 4 divisions, and we're going to bring this frequency down until we get to 2.8 divisions. So frequency. We're pretty much there. So what this tells us is that the pole due to CE is at 2.9 kilohertz. So the thing to keep in mind was that when we did this lab in the very beginning and we ran that signal at 1 kilohertz, what tells us is that 1 kilohertz was not really midband condition. It's really, you have to get above 4 or 5 kilohertz to get to that. Technically, this is 3 kilohertz. Technically, we should be more like 30 kilohertz to get fully into midband. So, but this says we have a pole due to CE. Remember, C1 and C2 are moved out of the way now. This is CE alone. We have a pole of 2.9 kilohertz. So let's see if we can see at what frequency that's going to start to level off. So pole frequency due to CE is 2.9. What we're looking for is this to come down and then stop coming down for a while. And it looks like it's continuing to come down. Okay. It's continuing to come down. So we may not be able to even see. We can turn our amplitude up, however, except that'll ruin our measurement, won't it? Not necessarily. Let's turn the amplitude up. Okay. I know this thing looks awful, but let's turn the averaging back on. Okay. All right, so what we're looking for is a range of frequencies where we're looking at a range of frequencies where as the frequency comes down, the output stops decreasing. So let's go back to frequency and see if it keeps on coming down. And it looks like the amplitude really, oops, not this one. Okay. So it looks like we're still at a little over 4 divisions. We're still a little over 4 divisions. So it looks like the amplitude is leveled off when we get down to about 40 hertz. So let's bring this back up and see if we can find a point where it starts to grow. So if this is 4.2 divisions now, okay, about 4 volts there, 4 volts going up by a factor of 0.707, 4 divided by 0.707. 4 divided by 0.707 is 5.66. We're going to look for the blue wave to get to an amplitude of 5.66, and that'll be approximately our zero frequency. So we're bringing the frequency up. Till it reads 5.66, and it's going to take a while to settle now. So we're still at around 4.6, 4.8. Okay, we're getting there, 5.44. Okay, so got to give it a minute to settle. 5.52. Oops. 5.68, we're pretty close. So according to this, we have a zero frequency of about 160 hertz for CE. So with that, we should have all of our frequency measurements there, and we should have something that you can compare with calculations and see what you get. And then the only thing left is to measure the value of R2 with the ohm meter, which we still haven't done. So this completes all the measurements. There was a lot of shenanigans going on with the oscilloscope. The oscilloscopes do not like looking at slow waves, and it showed lots of trouble with this. We had to resort to external triggering because these waves were not only slow, but they were small. And so we had to do a lot of playing with the oscilloscope to get these waveforms to show up. And even so, I'm not convinced that these are totally reliable measurements. So you're probably going to see some pretty large statistical errors. Don't take it personally. You've seen that there's a very kind of imprecise way of measuring these things. So low frequency response is difficult to measure. So let's just take out the pot for R2 and measure it, and then that should be the last thing we need, so you'll be able to get a value for RB. So I'm going to disconnect the power supply and turn this to ohms, and we'll see what we get for resistance of the potentiometer. Yes. So for the 10 potentiometer, we're getting around 8 point, let's try that again. About 8.4 kiloohms. So your R2 value for this lab will be 8.4 kiloohms, and you can use that to measure your RB and plug into your calculations. So that pretty much does it for this lab. Low frequency poles are difficult to measure. Next week, we're going to be doing high frequency poles, and those are much easier to measure. And what we'll find is that because we'd like to have a better bandwidth, we're going to replace all of these 1 microfarad capacitors in the circuit with a higher value, so that mid-band does go down to about 1 kilohertz. So next week's lab is very quick. It's just 2 frequency measurements and it's done. This is a more difficult lab. This has always been a difficult lab. But hope you'll be able to make sense of it. Okay.